Yeah, it's great to see so many people interested in mainframes. I'm actually a little bit surprised. Uh, yeah, because usually when you think about mainframes, the words that would typically come to mind are old and expensive, outdated, complicated. But you most likely wouldn't think about them in a cloud native context. And hopefully today I can convince you that mainframes are indeed still relevant for some use cases, and they also have their place in the cloud native and Linux world. These are the questions I'd like to answer for you today. So what are mainframes really? Because it's like a term that we throw around, but should have a common definition for that. Do they actually still matter? Is just banks using them nowadays? How do they work just on basic level? And then most importantly, the question most people will ask me when I tell them about the things I'm working on is, why would you put containers on them in the first place? And then we'll do a bit of a deep dive in how to actually do that. So aren't mainframes legacy infrastructure? Yes, but also no. I'll explain. So they're legacy because they've been around since the 50s. They still run COBOL workloads. Often they're tied to these old school institutions like the banks, the governments, insurance companies, etc. And a lot of their really old workloads are still running completely untouched for decades. And they're really not trendy at all. I mean, it's not really fitting into the move fast and break things kind of philosophy nowadays. Doesn't have the AI label on it to make it extra cool. So yeah, they're a little bit legacy, but also not, because they're still evolving. So modern mainframes can run Linux. They support cloud integration. They do also have AI accelerators now in some of the new mainframes, and are trying to kind of pivot into that whole hype thing. And they still process absurd amounts of data with better efficiency and reliability than huge racks of x86 servers. So these companies that still need that kind of crazy reliability, security, and raw transaction power still buy new mainframes nowadays. So they're not really going away. They never really left. They're just kind of invisible because they're not cool and trendy. But aren't they just big, expensive servers? Not exactly. They're more like the computing equivalent of a nuclear bunker. So in essence, they're ultra-reliable, high-throughput, and disaster-proof computers. And IBM actually tests the components against earthquakes and radiation. So they can technically withstand a solar flare and stuff. So the joke I usually tell people is that capitalism will outlive all of us because these mainframes will keep running the banking system. And a lot of innovation actually happened because of mainframes. So they have these battery backups and self-contained redundant water cooling systems. And that was actually the joke also back in the day. If you have a problem with your mainframe, you call a plumber, because it was just the first appliance to have that. And their hardware and firmware and OS are really super fine-tuned to work with each other and really built for these mission-critical workloads. Mostly, yeah, those are usually kind of impractical to handle on distributed systems. And the most common examples for these kind of workloads are credit card transaction processing, or withdrawing from an ATM where you don't want to have some kind of latency in between. You really want your things to happen really quickly. And speaking of credit card transactions, 90% of all credit card transactions are actually still handled by mainframes nowadays. And 71% of Fortune 500 companies still use them in some way. And apparently also all 70% of all prod workloads run on mainframes, while just accounting for 6% of the cost is the number. Okay, so I hope we have a basic common understanding of what mainframes are and that they do still matter, at least somewhat. Let's look at how they they work and what makes them special. So on a hardware level, all the components are really fine-tuned to work with each other and with super low latency and high throughput. And they can do really crazy things, like you can hot swap CPUs while the mainframe is running. And the SLA they built the mainframes for is 7 nines, which is 3 seconds of downtime per year, which is pretty crazy to me. And another cool thing about them is they have onboard crypto modules that are kind of like an HSM or hardware security module, and they can handle encryption and such related tasks all within the same device. And yeah, you could do a lecture series on all the special things about mainframe hardware, so I'll cut things short here though at these points. And then on a systems level, the key takeaways are that you can really just run all kinds of different workloads on them, either natively or virtualized in some way. And yeah, depending on the hypervisor technology used, with practically no overhead. So a few examples here. In this diagram, we can see KVM just running natively on Z. ZVM, which is their virtualization technology. ZOS is more the legacy stuff kind of things that has been really the standard for decades now. And then finally, we can also run Linux natively on an LPAR. And an LPAR is a logical partition of compute in the mainframe, which for simplicity's sake also kind of behaves like a VM, except it's below the hypervisor layer, closer to the bare metal part. And the mainframe has a type 1 hypervisor baked into the firmware, and each LPAR then gets direct access to a slice of CPU, memory, and I/O resources. And it's not time sliced like a typical VM. Okay, so we have a basic understanding of how the mainframe works, and we can make the jump to containers. Why would you want to run containers on mainframe? So one of the big reasons is modernizing legacy apps, so running microservices along old school COBOL without breaking things in between. Security and isolation is a huge part, so using the built-in encryption stuff for better isolation than your typical cloud infra. And it's also a big topic now again with the whole digital sovereignty discussions that are coming up. Low latency is another factor, so running these containers next to the big mainframe DBs equals faster transactions. And yeah, it's also a cloud alternative, really. If you can run Kubernetes or containers on a mainframe, you have cloud-like agility without really leaving your data center. And in the end, also cost savings play a role. So depending on the workload, running on a mainframe can actually be cheaper than running the cloud or on x86. The specific use case I'm working on is using confidential containers. Who has heard of Kata containers? Yeah, quite a lot of people. Yeah, there's a downstream product of that called OpenShift Sandbox containers, which is basically just Kata containers. And yeah, you can run these containers inside of a confidential virtual machine using the hardware-backed trusted execution environments of the processors. And normal containers are not really that isolated, and that's why we are really looking into that. They share the kernel, they trust the host, and Kata kind of fixes that by running each container in these lightweight VMs. And if you add the confidential computing tech to it, you now have confidential containers, and your apps run in a VM the host can't really peek into, even if the host is compromised. And yeah, it's made out of core 3 components that we really care about today. One part is the confidential computing itself with the CPU level features to encrypt memory and block host access. And the attestation to verify the workload owner is the container that is running in the trusted execution environment, and the encrypted image pools and file system. So the images and secrets can be encrypted and decrypted only inside of the trusted execution environment. And for my use case, we're using this IBM HyperProtect secure enclave for kata attestation, and then running the credential containers themselves on x86 actually. And IBM HyperProtect is based on the S390 secure enclaves and has like hardware-based isolation using these firmware-level crypto modules. Yeah, and in a typical kata deployment, you would have an external trust anchor, but this approach really allows you to have the whole system contained in one machine. Now, how do you actually put containers on mainframe? There are actually a lot of different ways to achieve this. You could run them natively on ZOS container extensions, which is something I found out while I was working on this. And ZOS container extensions is actually Docker Swarm under the hood, which I found really fascinating. But I'll tell you about the different ways that I use to put Kubernetes on mainframe in particular. So we'll take a short detour because a big differentiator on the software side of things and a bit of an initial hurdle is the systems architecture. If you remember when the Apple Silicon was coming out and a lot of things didn't work in the beginning and to some extent still don't really work the same way, we have the same problem with the S390 architecture where we can't just like lift and shift x86 workloads that easily. I wanted to explain the differences a little bit, and the first draft of this slide was just a table with side-by-side comparisons, but I found that really dry, so I'm going to use an animal analogy to explain the differences. And S390 is kind of like an octopus because you have the crazy parallelism of the tentacles that are all kind of independent but coordinated and can do crazy multitasking. Yeah, you can do slick hardware-assisted virtualization stuff, kind of like an octopus that can blend into its environment. And you also have crazy fault tolerance. Like an octopus can lose a tentacle and then regrow it. It's pretty impressive. And then x86, on the other hand, is kind of like a domesticated raccoon. It can do parallelism, but it's not always super clean when it does it. It's a little less efficient. It can try to do 10 things, but then ends up breaking something. And if it loses a finger, you have to take it to the vet. So this is the first scenario that I tried out, which is just joining a worker running on ZVM to an existing x86 cluster. And it's easy, right? It's just another Linux machine. You install some packages, you enable some systemd units, and it'll join the cluster, right? Yes, it's actually way easier than I originally anticipated. So this example here is just a vanilla Kubernetes machine on Ubuntu bare metal hosts, and then the Ubuntu ZVM. And the only challenge really was deploying the CNI to be multi-architecture and adding the right labels to the nodes. And then we can run cool workloads on S390. But there's more. There's a second way, because that was the actual way the customer wanted it. And it's almost the exact same scenario, but using an LPAR worker and an OpenShift cluster. It's easy, right? No. There are two fundamental differences that are kind of related to each other in these scenarios. For one, OpenShift uses CoreOS under the hood, which nowadays is Red Hat Enterprise Linux, meant to be immutable and optimized to run Kubernetes. And the second reason is that LPARs hate me, and by hate me I mean they're very particular about under what conditions they will or will not boot an operating system. And I'll explain this some more. If we just try booting an LPAR with a regular off-the-rack CoreOS ISO, nothing happens actually. Because to boot, we need two files. We have an instructions file, which specifies the kernel, the initial RAM disk, and an instructions file along with the memory load addresses. And then the parameters file, which just contains the boot parameters to start. So, like the points to the ignition files to partition the drive, set up networking, and all the other things that are kind of required to, in the end, join the cluster. Something you can spot here, actually, the parameter file needs to be on one line only. It only reads the first line, and I kind of found that out by trial and error. I was confused why it would only read the first param every time. But yeah, things I learned along the way. Also, CoreOS releases had a bug in them, and the bug is on the slide. And if someone can spot the bug, there's a little prize, maybe. Can anyone see it?
Is it the not scanning?
No. Does anyone have it? Okay, I'll let you know. So the path that is referenced does not actually match reality. So it's referencing a file that doesn't even exist. And apparently it's been this way since 2020. And I talked to the devs on Slack, and apparently I was the first one to ever try this, and it only affects CoreOS on LPARs. Yeah, but once we feed the LPAR all the correct parameters it needs to boot, we have a working ISO or working boot files. So how do we get that into the mainframe? So the mainframe has an HMC, or hardware management console, that is kind of like a BMC for regular servers, and you can use to manage them. And at first I had firewall issues, because the regular way you would do it is using SFTP, and you just boot over the network. But yeah, for the time being I had to like manually upload the ISO, and over a VPN that really takes quite a long time, and if you're trying to iterate fairly quickly and figure out which combination of ancient runes in the parameters file will make the system boot, it can be pretty painful. Yeah, and then eventually we did get the firewall to play nice, and we could load them over the network, which was a huge improvement. And the final setup looked a little bit like this, where we had the existing x86 cluster over here, and some artifacts were generated from an OCP endpoint, like the release files, some certificates, and ignition config. And then on first boot, the system, the ignition reads the configuration from this source of truth and applies the configuration. And you could technically boot directly from an ignition endpoint from the cluster, but we had to do some more customization magic in between. So writing a systemd service that runs at a very particular time in the boot process, after the boot process, to then trust the CA. And then from second boot on, the ignition endpoint is changed again back to the cluster. And yeah, this is the SFTP and HTTP server. So it's serving some of the artifacts over SFTP to do the initial boot. So it reads the instructions file and kind of takes everything from there. And then some of the other things are loaded over HTTP. Yes, so that's the LPAR fetching the instructions and then deriving everything. And the install target is an attached fiber channel storage system, because using the onboard storage would be too easy, of course. But these diagrams can get a little bit abstract. I'll show you what this looks like in real life. So this is the back of the mainframe, actually, on the left side. The top part is the HMC, so that is what we've been using to interact with the system to get it to boot. And then in the middle, we can see the fiber channel storage that is hooked up directly to the mainframe. And then I didn't think of this when I was in the data center taking the picture, but on the right side, there are the x86 racks, and you have to trust me that they're there. Okay, so we got the system to boot. This is a major step into the right direction. And we can observe the install process from this beautiful modern console. And it runs through, it installs the system, and after the initial install, we just change the boot source from SFTP to SAN and reboot, kind of like when you're installing an operating system at home and you take the USB out and boot normally. And then with those hurdles overcome, we can get a certificate signing request in the cluster, approve it, the node joins. We've come really far, but things can still go wrong, actually. So I got this far a couple of times, and some daemon sets then wouldn't start. But those are all problems that we can then solve with setting the right kernel parameters during the install. So I'll spare you all of those details. Now, equipped with all that knowledge and experience, the process is actually not that hard anymore, but things are always a little bit harder when you have to figure them out with no documentation for the first time. But yeah, we have a worker joined to the cluster on S390. Hey, it works. So to wrap this up, we've learned what mainframes really are. We've established they still matter for some use cases. We learned a little bit about how they work, why you would put containers on them, and how and how not to put containers on them. So what is next? So maybe this talk got some of you interested in learning more about obscure infrastructure, mainframes. And I've compiled a couple of resources here for you to get more information about these modern mainframes and confidential computing. There's this open mainframe project. It's actually an initiative run by the Linux Foundation. And part of that is this Ambitus project, which focuses on porting open source software to mainframe architecture, which is really interesting. And you might be saying, well, I don't have a mainframe at home. How am I going to do mainframe stuff? There's the Linux One community cloud where you can actually get a ZVM instance to play around with stuff. And if you have an open source project, there's also a form to apply for a longer term one, and you can get multiple instances to play around with. Yes, and then finally there's the OpenShift sandbox containers documentation, which is quite interesting if you're interested in Cocoa. Yeah, with that we're already at the Q&A part. Oh yeah, that's me with the mainframe, but from the front actually. Great.
Do I need a mic? No, can I just yell?
I don't think there's anyone here with a mic. I'll repeat the question for the recording.
So if the mainframes in general are good at being reliable computers, basically, isn't that an ideal use case for the control point, actually? Did you try that?
Okay, the question was, since mainframes are so reliable, whether it wouldn't make more sense to use them for the control plane. That is a good point, for sure, yeah. It's, it wasn't considered in this particular use case, but sure, yeah, it makes sense. Question over there?
Do you have a rough indication on how many container images are available?
Like from big projects, like Postgres or something like that?
Okay, the question was whether I have a rough estimation of how many container images are available for S390. So a lot of the big ones actually have S390 images. Yeah, Postgres was an example that does have images. I looked around a little bit on Docker Hub. There's a tag for S390. But yeah, I'm not sure. If you run an open source project and you'd like to also provide builds for S390, then please do.
You mentioned that it was quite hard to get it done because the documentation wasn't there.
Yes.
Did you fix it?
It's in review. It's been in review for about a month. I'm waiting for them to actually publish it. Yeah.
So is this just something of interest, or is there an institution or customer who actually wants to do this?
Yes. So this was for a hyperscaler customer that is doing that.
Right, just one.
Well, that's the one I worked with. Yeah. Yep, on the front.
Did you do any performance testing in comparison between the x86?
That is a question that has been asked before, actually. Not at this talk, but a different talk. Someone asked this before, and I said I would do it. I haven't gotten around to it yet, but it's on my list somewhere. Yeah, I wanted to like run some kube burner tests and then have like some actual data to compare. Yeah.
Stupid question, probably. I don't know if you can answer it, but how many technologies are even able to compile to S390 anymore besides Go and probably loaded stuff like Rust and C?
Also an excellent question. So I did some other C mainframe things that no one asked for, and kind of ran into that problem. A lot of C stuff works pretty well, like natively, if you have an S390 system and then you just build things on there. There is also the option of technically working like with cross-compile stuff. In my experience, doesn't usually work that well, and you have problems with how you link libraries, and yeah, it's not that fun. Yeah, in the Open Mainframe project, there are a couple of different efforts to kind of improve these things. I think a lot of them are around Java, actually. I'm not a huge Java fan, but that's what it is.
But Clang exists, right?
Pardon?
You have UCC and Clang.
Yes, yeah.
Probably just to follow up on
Yeah.
that, I mean, it is kind of hard because most of, as you said, cross-compiling is kind of hard, and there is no GitHub runner available.
There is now, actually.
Actually?
Yes.
I haven't said anything.
That's a good question. Yeah, no, it's been that way for a while. But previously, you had the option of technically getting an instance for yourself and then setting up a runner on that. But IBM also actually offers managed runners now for open source projects. Yeah.
Follow up on that for what in general, what tooling has been or has been made available as of late. So we have runners. Are there other instrumentation that's been made available in some way?
Can you elaborate a little bit on what you mean?
Well, I was thinking, I'm not sure I understand. I don't think I fully know what I was asking, to be honest. Never mind.
That's fine. Yeah. Also.
Can I ask about, so IBM has the Tellurium, its AI accelerator for the mainframe?
That might be the brand name for it, yeah. I don't work in tech sales, unfortunately, so I don't know all of them.
If you want to run AI workloads, what is available?
I'm not sure I can answer that question, to be honest. I'm sorry. All right. Yeah, I'll also be around at the tables in the front for a while if you'd like to talk about some more. I'm actually quite surprised a lot of people were interested in discussing this, so happy to keep the conversation going.